Hidden along the coast of England is a project that once seemed almost impossible. Its scale and complexity go far beyond most things humans have ever built. This is Hinkley Point C, a nuclear power plant being constructed with enough concrete to build an entire small city. It represents one of the most ambitious engineering construction efforts in Europe in the 21st century. With a total cost of more than £30 billion and a construction timeline that has already stretched over more than a decade, Hinkley Point C is expected to supply electricity to millions of homes while playing a major role in reducing carbon emissions. So how can people turn such a high-risk idea into a massive energy-producing machine? To understand how Hinkley Point C is being built, it is important to first look at a major challenge facing the United Kingdom today: the energy crisis. For many decades, the UK relied heavily on coal and natural gas to generate electricity. However, as pressure to reduce carbon emissions increased, many thermal power plants have gradually been phased out. At the same time, renewable energy sources such as wind and solar have expanded rapidly, but they are still not fully stable. When there is no wind and no sunlight, electricity supply becomes less reliable. This large gap in the energy system has forced the UK to search for a power source that is both stable and able to meet environmental standards. Nuclear energy therefore became an almost inevitable choice. From this need, the idea of building a new nuclear power station emerged, and Hinkley Point C became part of a long-term strategy to strengthen national energy security and support the country's net zero emissions goals. However, alongside this ambition comes enormous risk, especially in terms of construction costs and technological complexity. Hinkley Point C is being built on the southern shore of the Bristol Channel in Somerset. Covering an area of nearly 2 million square meters, it is considered the largest construction project in Europe. Its scale is so vast that its predecessors, Hinkley Point A and Hinkley Point B, which operated from the 1950s and 1960s, now appear small and outdated by comparison. Hinkley Point C is designed around the EPR reactor, European Pressurized Reactor, one of the most advanced and complex nuclear technologies ever developed. The result is a multi-layered safety structure, where each system can replace or support another if necessary. This is not simply a plant designed to operate efficiently. It is a plant designed never to be allowed to fail. The coastal area of Somerset has weak soil conditions, high moisture content, and is continuously affected by tidal movement from the Bristol Channel, making it unsuitable to directly support a massive nuclear power plant like Hinkley Point C. Because of this, before construction could begin, engineers carried out a large-scale ground improvement program that included installing approximately 29 kilometers of steel piles, driven up to 12 meters deep, to create a stable foundation for the entire structure. At peak construction stages, more than 2,000 workers were operating daily on site, transforming a quiet stretch of coastline into a large industrial construction zone. 2 high-capacity on-site concrete batching plants were built, along with dedicated transport routes, a heavy equipment jetty for oversized deliveries, and long-term logistics facilities to support continuous construction operations. Once the ground stabilization work was completed, the next phase began with pouring the plant's foundation structures. These massive concrete base slabs had to meet extremely strict precision requirements because even small deviations in elevation or material performance could affect the installation of sensitive nuclear equipment later. In particular, the reactor area, often described as the heart of the power station, required a foundation that was both exceptionally thick and extremely stable. To guarantee quality, the concrete was produced directly on site and carefully controlled for temperature, moisture levels, and material composition. During some peak construction periods, thousands of cubic meters of concrete were poured continuously over several days, forming foundation structures capable of supporting enormous loads throughout decades of operation. Alongside the massive structures built above ground, another equally critical part of Hinkley Point C lies hidden beneath the Bristol Channel. This is the seawater cooling tunnel system, a large-scale underground infrastructure that plays a vital role in the operation of the entire power plant. Engineers constructed tunnels stretching for several kilometers beneath the seabed to draw seawater into the station and discharge it after heat exchange with the reactor cooling systems. These tunnels were excavated tens of meters below the seabed, where construction conditions are far more complex than those encountered on land. At key connection points, large vertical shafts were installed with extremely high precision to link the power station to the underground tunnel network. This became one of the most challenging parts of the project, as the work had to be carried out under high-pressure conditions, within complicated marine geology, and with near-absolute positioning accuracy. Once completed, the system forms a large-scale cooling water circulation route that allows the plant to maintain stable operating temperatures for its reactors throughout a service life expected to last several decades. In a nuclear power plant, the most complex and critical area is always the reactor zone. This is the center of the entire system, where safety standards, structural requirements, and quality control procedures are applied at the strictest level across the entire project. For this reason, the first step in constructing this area is building the containment building, the massive protective structure that surrounds the entire reactor. The containment structure is not constructed through a single concrete pour. Instead, it is built layer by layer and segment by segment. Large-scale formwork systems are installed first, and concrete is then poured floor by floor. At the same time, an internal airtight steel shell, known as the steel liner, is installed piece by piece alongside the outer concrete structure. This liner ensures the containment building remains completely sealed and prevents any radioactive leakage under all operating conditions. Each steel plate must be welded with extremely high precision and inspected using ultrasonic testing and X-ray scanning before final approval. Only after the containment structure reaches the required levels of stability and airtight performance under nuclear safety standards does the interior space become ready for the next phase, installing the reactor's critical equipment. This step-by-step construction process, carried out under strict control at every stage, ensures that the entire reactor system is placed inside a structurally secure and fully verified safety environment from the very beginning. Once the reactor structure had been completed, the project moved into the next major phase, the installation of the nuclear equipment. This process followed an extremely strict sequence. First, the largest and most critical component, the reactor pressure vessel, was positioned at the center of the reactor building. Weighing several hundred tons, this component required heavy lift crane systems and alignment operations carried out with near absolute precision. Once the vessel was secured in place, the rest of the reactor systems were installed around it. Next came the installation of the steam generators, the primary circuit piping system, and the heat exchange equipment. These components form the network that transfers energy from the reactor core to the rest of the power plant. Every connection had to meet absolute sealing standards to withstand the extremely high pressure and temperature conditions during operation. Hundreds of kilometers of piping were installed, welded and inspected using non-destructive testing methods to ensure that no defects remained within the system. After that, the turbine hall was constructed and equipped. Steam produced by the reactor drives the massive turbines, converting thermal energy into electrical power. The generators installed here are enormous in scale, with the capacity to supply electricity to millions of households. Finally, the entire electrical system was connected to the national grid through high-voltage substations, transforming Hinkley Point C from a construction project into an active component of the country's energy infrastructure. In addition to the reactor area and turbine systems, Hinkley Point C also includes a wide range of large-scale supporting facilities, components that do not directly generate electricity, but are essential for ensuring the plant can operate safely and continuously for several decades. Among these are the spent fuel storage buildings, constructed with thick reinforced concrete structures designed to provide complete radioactive isolation in accordance with strict nuclear safety standards. At the center of the plant's operational system is the main control room, the location where engineers continuously monitor the station's operating status through thousands of real-time data signals. This area functions as the brain of the entire complex, allowing operators to supervise everything from reactor temperature conditions to cooling systems and outgoing electrical network performance. However, for a nuclear construction site on the scale of Hinkley Point C to operate continuously over many years, dedicated infrastructure for the workforce must be developed alongside the technical structures. Next to the construction site, a large staff support area was built to serve thousands of engineers and workers operating in continuous shift rotations. This area includes accommodation facilities, industrial dining halls, medical services, fire response units, and operational support services functioning 24 hours a day. At peak construction periods, tens of thousands of workers were active on site, turning Hinkley Point C into one of the largest construction sites in Europe. To sustain this pace, the entire project area was connected through a complex logistics network of dedicated transport routes, material storage yards, and continuous supply systems, ensuring that materials, equipment, and workforce resources remained available for every upcoming stage of construction. Hinkley Point C is the first nuclear power plant the United Kingdom has built in several decades and was expected to open the way for a new generation of energy infrastructure for the country. However, the reality has been far more complex. From the very beginning, the project faced controversy and opposition from several organizations. Concerns about cost, safety, and long-term effectiveness repeatedly affected the project's progress. At the same time, construction costs continued to rise, and the project is now expected to become one of the most expensive nuclear power plants ever built. Originally scheduled for completion in 2027, with an estimated cost of £26 billion, the plant is now unlikely to begin operation before 2030, with total projected costs revised to between £31 billion and £34 billion. In a message to workers at the construction site, the chief executive of Hinkley Point C stated that the COVID-19 pandemic alone caused a delay of about 15 months. Throughout the construction process, the coastal ecosystem of Somerset has been significantly affected. The construction of seawalls, the excavation of tunnels beneath the seabed, and the transport of massive volumes of materials have altered the natural landscape and impacted marine species and surrounding habitats. In particular, the plant's cooling system uses a very large amount of seawater each day. After passing through the cooling system, this water is discharged back into the sea at a higher temperature, which could affect the marine ecosystem if not carefully controlled. However, engineers have implemented multiple measures to minimize these impacts. Filtration systems were designed to reduce the risk of marine organisms being drawn into the intake pipes, while the temperature of the discharged water is kept within safe environmental limits. From a broader perspective, Hinkley Point C is also considered part of the environmental solution. Once operational, the plant will provide a large supply of low-carbon electricity throughout its service life, helping reduce dependence on fossil fuels. To reduce long-term environmental impacts in the future, society must accept certain environmental trade-offs in the present. Hinkley Point C is not just a massive construction site. It is a clear example of how humans are reshaping the energy system in the 21st century. From a quiet stretch of coastline in Somerset, the site has transformed into one of the most complex infrastructure projects in Europe, where tens of thousands of engineers, workers, and heavy machines are working together to build a new generation nuclear power station with safety standards unlike anything seen before. Despite ongoing debates about cost, technology, and long-term risks, Hinkley Point C continues to play a critical role in the United Kingdom's strategy to secure energy supply and reduce carbon emissions for decades to come. Once completed, it will not only provide electricity to millions of households, but also raise a larger question for the future. Will nuclear power continue to remain an essential part of the modern global energy system? What do you think about this choice? Share your thoughts in the comments below. And if you would like to explore more mega projects like this one, don't forget to like the video and subscribe to Mandarin Tech to follow our upcoming stories.